Okay, cool. So, hello to my presentation, Engineering a ROP-chain against Node.js. A bit about who I am. My real name is George, but I usually go by Kriel in the hacking CTF community. I work as a vulnerability researcher at Census, primarily focusing on browser security. I've been a CTF player for a bit more than 4 years, on and off, but mostly on. I'm a co-founder of IORS, which this blog post is a part of. I'm going to talk more about it later. And in general, I very much enjoy low-level stuff. I come from a reverse engineering background, but I also like exploitation and whatever comes from it. So this is the agenda. I'm going to do a small introduction about how we got here. I'm going to do the technical background analysis on our target, which, as I said, is Node.js. I'm going to go a bit over the vulnerability that was found and exploitation overview. Then we're going to go deeper into exploit development. I'm going to hopefully do a working live demo, and we're going to finish with some takeaways and a conclusion. So the introduction is the whole thing started, unfortunately, not from me, but from Stefan Schiller in October 2024, while he was working at Sonar Research, where he did some research on exploiting Node.js on hardened environments. We're going to talk about what that means. I focused more on the exploit development side, but it should be noted that a first POC was developed by a CTF player known as Jordan Walter. So kudos to him for that. In December 2024, a good friend of mine, Lin, who's here, approached me to develop a proof of concept exploit for a CTF challenge while he was working at Hack the Box. We were also discussing about making a blog where we can post research write-ups. That is IORS, and we did that on mid-April. And by, I think, mid-July, Mixie had contacted me, rather he told about the conference being held, and if I wanted to, and if people wanted to present, I was cool with it, so here we are. So the reason why I like the idea of presenting this is because I think it has meaning both for CTF players and general tech people, because what I'm going to present is something that kind of shows that even if you have a popular, stable framework to write code, you don't really guarantee security with that. There are many different ways that hackers can exploit software without you actually understanding how that might work. It's all about the underlying mechanisms of the software that we're going to talk about. And for CTF players, it's nice because you can learn how to cheese web challenges. So let's go over the technical background for Node.js and what we care about. Node.js, I'm pretty sure everyone's familiar with it. It's an environment that generally extends JavaScript beyond browsers. You usually wrote JavaScript for just client-side stuff to handle events. But through Node.js, you can use it to write command line utilities. You can use it to write backends. So it extends the language a lot. For the pure JavaScript part, it uses a JavaScript engine called V8 to parse and execute JS internally. However, there's a lot of stuff that goes with actually communicating with the operating system, handling file system calls, signal handling, and many more stuff. So how exactly does Node.js do that? And the answer is a component called libuv. Libuv, I should have changed the D. It enables asynchronous input-output, which essentially means that, hold on. Hello? Okay. Which essentially means that it just handles what we just said, like communication with the operating system asynchronously. And also provides a thread book for blocking operations. So what happens is that there's an event loop, which is running all the time, in which events are registered on a queue. And when the front event is ready and no event is being handled, then that is passed to the handler, and that is processed through a callback that has been passed to the event. We're going to see more about how that is actually in code. And the way that these are passed is an anonymous pipe is exposed. Anonymous pipes are IPC mechanisms used in Linux. I'm pretty sure that Windows does something similar to it. And probably what we're going to discuss about is applicable to Windows. However, you would have to do a bit more different research. And yeah, the IPC mechanism is used for communication between the main process and the spawn child processes to the main Node.js process. This is just a small symbol that I wrote for a method, just to show that you can go there and have a code sync that leads to the snippet that we're going to discuss about, just so that you can actually see the flow that an event could potentially take. But we don't really care about it, so that's why I just left it as it is. If we do an ls in the proc file system, then we can see the different file descriptors that are available. And for example, 10, 11, those are the anonymous pipes. So instead, what I mean by that is that procfs is usually a file system that, especially in CTF challenges, for example, we kind of care about it because it lets you do a lot of cheese stuff with it, and it's generally accessible. It's something that is accessible even in hardened environments. We're going to discuss about it right now. In terms of Node.js, right, if we have a Node.js application running, we can potentially access the procfs file system through an arbitrary file upload primitive. This is something that Sonar faced in their initial research. They were faced with a hardened read-only environment, so they couldn't, just write files, which, for example, to write their own SSH keys or stuff like that. But they had the arbitrary file upload primitive. And so they thought, okay, how can we use these anonymous pipes to do something malicious? And so what they did was they decided to check the source code of libuv and hope that somewhere along the road, the data that they could send, and if they send data to an anonymous pipe, because it's a file descriptor, it would just read it automatically. So it wasn't really that difficult. So they hoped that something might allow code execution. So let's see. We're going to go over the vulnerability, and I have it in quotations because, as you will see, it's really not that much of a vulnerability. It's a bit of a feature, so to say. This is the relevant snippet. This is found in libuv source Unix signal. For Windows, it's libuv source Windows signal. In the UV signal event function, as we see, we have some couple of internal structures like signal message, signal T, and a char buffer, where the data is stored from the pipe FT, right? This is the event loop that we talked about, and it accesses the file descriptor, and you just read from it and stores our data into buffer. The important thing is that these are attacker control data. So if we do a bit of taint analysis and see what we can control the buffer. After that, it just accesses this for loop, and then we can control both message and handle. So if we see the checks that are being done further down, we can easily bypass this because we control both values, and we can also bypass that assert, and we reach the vulnerable line, which accesses the callback that we mentioned through the handle variable. And this is an attacker-controlled function pointer, so we can essentially pass to any function that we want, any address that we want, and we can redirect code execution through it. So essentially, this is a vulnerability that easily gives an attacker control of the CPU, of the instruction pointer, and we can redirect control execution wherever we want. So it's a very powerful primitive. Hello? Okay. Which can give a lot of control over how we proceed with exploitation, and we don't really have to care about finding any other vulnerability because that's what we care about, getting instruction pointer execution. So, but as for exploitation, as I said, we have a controllable function pointer. It should be noted that Node isn't compiled with Pi. Pi is not really a mitigation, kind of, but it's essentially that instead of having the binary compiled at constant addresses and being loaded at those addresses, it's being accessed through offsets that are being loaded at random addresses in the computer, right? So that is being connected with ASLR, which essentially randomizes the addresses at which the process is being loaded. So that essentially allows you to not know any of the addresses of stuff inside the runtime beforehand. But with Pi, we know where everything is loaded inside the process, inside the actual Node.js binary. So that's very useful, as we'll see. Exploitation is not so straightforward in the sense that it's not like we can think of it as handle, system, and then bin sh that we pass. We need to do a bit more stuff with it to actually gain a shell, for example, to gain rather command execution on the actual system. And so usually for that, what do we use? We use ROP. So I'm going to do a return-oriented programming primer in case people are not that familiar with it. So return-oriented programming allows us to construct sequences of operations to perform arbitrary objectives, right? So for example, if we want to write somewhere to memory, if we want to call functions, ROP is an exploitation method that lets us do that. It requires us to have instruction pointer control, which is what we have. And the fundamental unit of ROP is gadgets, which are small sequences of assembly instructions found inside either the target binary or some linked libraries, essentially anything that's inside the process runtime. And we can use those to essentially start and construct those arbitrary objectives that we want. And this is a very small example of a gadget. This is a very popular one. It's pop RDI red, and it essentially lets us get the value from the top of the stack and push it into RDI. And so with that, we can control RDI, which is usually the first register that is being used as the first argument from the calling convention on Linux. However, a quick note on the gadgets that we care about. Because as you see here, we have a couple, like what we're going to pass first has a couple of restrictions. First off, we need to have the signum, we need to pass this check, and we also need to pass a valid callback at different offsets. So for example, to bypass the assert, we need to have the LSB set to 1 at offset x8. We also need to have a valid pointer, which points to a good gadget at offset 60. And this is more Node.js restriction, which is the most important one, is that we are not allowed to use any byte that we can. We are constrained in the range from hex 0 to hex 7e, which is due to just how Node.js works. Specifically, this is going to be the emulated file upload functionality that we're going to use. And so we can see that and this is also what Sonar, what was used in the Sonar research, so I tried reproducing it as closely as possible. So this is the function that was used, and this is what restrains it to this byte range. So we're very much restrained into what bytes we can actually use, and so we're going to have to do manual filtering both in finding our initial gadget and also in finding the rest of the gadgets so that we can produce a valid exploit. So to automate the discovery of the first gadget, because it's kind of specific, Sonar Research spent a good part of their write-up on actually how to do it, rather than the actual exploit development. So I kind of reproduced what they did. So what I did, I'm not going to show the code because it would take a bit too much, but essentially I used phone tools to parse Node and find all the executable segments. And then I went through them, just found interesting gadgets that just ended in red. And if they were valid addresses within the range, then I just dumped the instructions with capstone. And we're going to see the gadget that we came up with soon. Lastly, before we go into actual exploit dev, the Node.js version that I was targeting was version 22.9. You can find either a tar available from Node.js, or you can just build it from source. Either way, you can get it easily with debug symbols, which kind of helps with debugging. And yeah, we're just going to use a simple upload server and exploit runner taken from the Sonar Hexacon talk. To display that, I'm going to show them in a bit. So let's go over exploit development. Of course, in order to get command execution, we need to actually use a command that lets us execute code, like for example, system or exec_vp and stuff like that. So let's go around and search if any of these symbols are loaded into the Node.js. And as we can see, we only have execvp, which is at address E0, AD10, which unfortunately isn't a valid address based on the range that we discussed prior. So we cannot really use that. So another idea was, okay, what if we use syscalls, right? Syscalls are also command execution mechanisms. We have, for example, the execv syscall. So if we can use a syscall gadget, which essentially just uses the syscall instruction, then we can do just that. This was the best gadget that I found. However, as we can see, this also isn't in a good address range. So we don't really have any good candidates with which we can proceed. So what I did was, okay, well, let's see how they are called, and we'll figure it out as we go along. So this is the call prototype. This is the syscall ID. Syscall, it has an ID to it that's identified, and the first argument is the file, a pointer to the file name. The second argument is a pointer to the argument vector, and the third is to the environmental variables, which we really don't care about. This is honestly something that ChatGPT produced to just have some manual call of an execv syscall. And I did this mostly to just see how in memory it would be stored. So as we can see, this is where the syscall is being called, and we have a pointer to the whole argv that it wants. As we can see, the first pointer is the actual program that we want. And then we have the second pointer that is the argument. So that's kind of the layout in memory that we wanted to have for our exploit as well. And through seeing this, we actually understand a couple of further problems that we have, because we actually need to know the pointers beforehand. That's the main problem, because we need to reference things in memory, but we can't really know that because, for example, we can know the addresses of the stack beforehand, so we can really easily reference stuff in memory. So that's kind of a big problem, and we can't really have a leak because this is just one write, right? This one file upload. We can't take a pointer back to have an info leak and use that to calculate base and stuff like that or whatever, and just redo that again. We have only one attempt, so that's kind of a difficult thing to try to solve. However, not that much, because as we said, Node.js isn't compiled with Pi. So we have a lot of addresses that are static, and some of them are writable, like, for example, the .bss section or the .data section, right? However, it would be really, even though it would be really nice if we can just, write something there, the problem is that we still have only one write, and that is on the stack. So that's another problem. How do we bypass that? Which is kind of easy concerning what we discussed so far, because if in theory we can call any syscall, then for example we can just call sysread, right? And we can easily redirect execution to just do sysread through ROP-chain. So what we can do is we just call sysread firsthand, read the actual payload that we want, right? The execv data, and we just pad the ROP-chain with the execv data. And the reason for that is during the first read, we have hex 200 bytes that we need to fill, right? So for example, if the ROP-chain is hex 100 bytes in length, then for example, we need to pad another hex 100 bytes so that the execv data are not stored with the ROP-chain, and they are in the buffer that expects input. And when a read operation is executed, then that will be stored where it will be specified. So we need to add a padding to it, to our last payload. So this is what I said. We're going to send our ROP-chain plus data, and we're going to use sysread to store the execv data, and then we're going to call sysexecv. So now it's time to actually find our gadgets so they can start implementing our attack path. As we said, the first gadget was discovered with the approach we previously mentioned. But the rest of the gadgets, because we don't really have to do that convoluted stuff we need to bypass checks at different offsets and have a pointer to it, we can just drop everything with wrapper, and we can just grab for interesting gadgets and valid addresses. So this is the initial gadget that we want. At offset hex 60, we can see that this is the function, this is the callback, right? That will be defined, which is just a gadget that does 3 pops. This is also its signum, and yeah, it's the initial gadget that was described earlier. And like if we think about it in terms of how ROP works and what we discussed, we just want gadgets that can help us control all the arguments that we've talked about. So, for example, we need a pop RAX to just specify the syscall ID that we want to call. We need a pop RDI to control the first argument. This has the SBB, instruction. We don't really care about it because it doesn't affect us that much. But it still shows that, for example, because we can't use any address, we had to make some compromises in terms of what gadgets we had to use. A pop RDX gadget, and this is actually the same gadget as was specified in the callback. I didn't find anything else because it's just simple and we control RSI with it. We have to pop junk values into R15 and RBP, but we don't really care about that. And this is so far the easy stuff, but the more difficult part was, okay, we still need to somehow deal with the address of the syscall gadget, because we cannot really just go ahead and use that because it has a bad address. So what I thought about is, okay, we need to find a couple of gadgets that dynamically change, change the address of the syscall gadget to what we want at runtime and push it on the stack so it's available to us while the ROP-chain is being executed. So we need to find relevant gadgets for that, and these are the gadgets that I found. The first one is a sub gadget that just is the operation that we want to convert to get the value that we want between RX and RDI. And push RCX is the gadget that's going to be used to push the value of syscall, the syscall gadget to the stack. However, we still need a bridge between RAX and RCX, and this is what the last gadget does with the move RCX RAX. This is the best one that I found, honestly. And even though it might seem that it might have some restrictions, this is actually not the case because we control both RDX and RDI. So we do not have to. So we can control this jump not equal and not take it, so we don't mess up with our code flow. And also this dereferencing to store the value of null. It's not really a problem because we can specify a valid address at RDI, so that also doesn't become a problem, right? The program doesn't crash just because of an invalid dereference. So we can easily use that to connect everything together, and these are all the gadgets that we used. So the last question is, how do we connect all of them? And this is the final flow of the chain. We initialize the ROP-chain with the first gadget. We construct the syscall gadget, right, with the way that we viewed so far. We populate the registers for a sysread. We push the syscall gadget onto the stack. We execute the read syscall, and then we do the same thing for the sysexecv, while we also construct the execv command line data as it expected to have it. Some notes on debugging. After I got sysread, that meant that I could, get an arbitrary syscall executed. In terms of actual command execution, I tried initially to get a shell, right? So which wasn't good. After that, I tried to actually have a simpler command executed, like touch, for example, which just creates a file, which was much better to actually understand how execv expected its data. And after getting this execv to work, it was just a matter of finding a good, like a reverse shell payload to get it work. So in general, like try to do simpler stuff to just get a proof of concept actually ready, and after that you can go ahead and do the cool stuff with code execution. So now we're going to do the live demo and hope it works. So we're going to need 3 terminals, right? And for the first one, actually, I'm gonna read a couple of notes that I had. Talk notes. Okay, so this is gonna start up the server, which is what we had seen before. Right, so we have a server running with a file upload at port 3000. And now we're gonna pass the command that we want to our exploit. Let me show you the exploit a bit as well. Right, so these are all the values, the relevant values that we wanted for one reason or another. We can see, for example, the signum, some syscall IDs, and stuff like that. These are all the gadgets that were used. These were all the relevant functions for the operations that I mentioned. This is how the exec_v, this is the function that constructs the exec_v data. And these are the step-by-step operations that we're going to do. And we're just going to write the ROP-chain into a payload.bin. Test. Okay. And test. What was the instruction? Command. Test. Right, and this is just a sends a post request. Come on, test. Okay, and this just sends a post request, and we do a path traversal, as you can see, to the pods. Come on, test. 1, 2, 1, 2. Okay, gonna make this quick. So did I copy it? Yep. So let's run it. As we can see, this is the ROP-chain has been constructed. One, two. Okay. And let's also open a netcat listener at 4242 because that's the port that we specified. So if we run one, two. We got a shell. So yeah, we got a shell. So it works. As we can see, it doesn't also crash Node.js, so that's good. So to wrap it up, some takeaways in conclusion. So a good question is, whose problem is this? Is it libuv? Yeah. Okay, so is it libuv or Node.js? I'm more of the opinion, and I think that's kind of the correct, that Node.js is kind of responsible for this because it's a whole architectural design choice that they have with how even in hardened environments you can still achieve that. For example, Node isn't compiled with Pi. Thank you. They've kind of discussed that in an open issue, and they don't compile with Pi because of performance reasons. However, as we can see, command execution is pretty severe. And also, even in hardened environments, they don't restrict the capabilities of an arbitrary file write. We can just easily write anywhere, so that's also kind of a problem. So they kind of need to change how they deal with that. And in summary, I really wish I had found everything. As I said, the whole actual idea was found by Sonar Research. I mostly did exploit development stuff to create a proof of concept. Whatever software you use, you can be safe, but you can never be 100% safe. And it's very important to actually know about low-level stuff and concepts because you never really know who's out to get you and how he can get you. And to conclude, research can be done in developing a tool for automatic exploit generation. There are many versions of Node.js that are still vulnerable with this. I don't think that they patched it to the latest one. So if there was a tool that could generate ROP-chain for any Node.js version, that would be kind of critical, and you could definitely mess with a lot of servers. And also libuv is used by different other languages. like for example, Julia, Lua. So those languages might be vulnerable as well. So yeah, there's still more to do in terms of actual research on this. Thank you. If you have any questions at any point in time, I'm free to answer them.